Hey, welcome back. Today we will discuss this important topic, damping coefficient modeling, inverse Fourier transform of impedance. So just before entering the topic, hey there, this topic is pure theoretic experimentation or abstraction, above all for the external damping part. The internal one, incredibly to say, it's more probable it exists because of the nature of the phenomenon or the equation of motion. However, no tests have been made, so I'm talking purely doing suppositions. As always, English is not my native language, so advices to improve are welcome. Summary. What we will discuss, a quick recap, inverse Fourier transform of zeta or impedance, damping coefficient real part frequency independent case, then damping coefficient real part frequency dependent case, final recap and conclusion. A quick recap. Alright, so straight to the point I want to discuss in this video, I'm talking of this equation of motion that maybe should become this one, where in place of the damping coefficient there's the inverse Fourier transform of impedance, where zeta is this one, that is impedance, which is the damping coefficient and the two mechanical reactances. I talked in a previous video that I will link in the description or maybe in the upper right corner. So zeta impedance is composed by two parts. One real part, I call external to the system, where for system I mean the poor oscillator, so external to the system damping, and one imaginary part divided in two subparts that are the reactances that are intrinsic to the system. The reactances are for sure present into the system because if you take a pure oscillator, they are already there. So this is the equation of motion in case damping is not present. With the usual substitution, we end up with this relationship, with this formula, that eventually leads to the impedance, this formula for the impedance. The doubt I had in the previous video was the fact that once you multiply those two terms of the impedance by j omega x, you return to the elastic force and inertia, so without having a damping term. So I came up with the idea, this is the idea, that we have to compute the inverse Fourier transform of these two terms to put it in the equation of motion, to put them in the equation of motion in time domain. But the two reactances, one seems to be frequency independent, the elastic one, and once you multiply it by j omega x, and the other seems to be strongly dependent from frequency because of the second power. But I'm really confused on this point, so further investigation is needed. Right before going with the inverse Fourier transform of the impedance, talking about the real part, it could be frequency dependent, serious problems for us, or constant, that is to say frequency independent. We don't know this a priori. So to sum up, the impedance is divided in a real part and imaginary part. There are two reactances. The real part maybe is frequency independent, maybe is frequency dependent, we don't know. The imaginary part, one part is frequency independent and the other one is frequency dependent. So inverse Fourier transform of zeta or impedance. Now I'm not so good at Fourier transforms, but the two inverse Fourier transform of the reactances should be, and please help me and check these formulas. This one for the elastic reactance that ends up in being k on 2 or k over 2. Please give me advice on this. Times sines of t. And the inverse Fourier transform of the massic reactance is eventually mass times derivative of delta function, where delta apostrophe is the derivative of Dirac distribution and is equal to two impulses, one opposite to and right after the other one. And here's the derivative of delta taken as a Gaussian pulse with a variable width. This is the image. As you can see, they are two pulses, one opposite to each other and one after each other. One before the zero, the center of the impulse, so one after the zero, the center of the impulse. As you can see, the situation is becoming interesting. Remembering we are forcing outside the resonance because in resonance the two reactances cancel each other. Until this moment we are in this situation. This is the equation of motion in which in the square brackets there is the time domain somehow. There's Fourier transform of impedance, the two reactances. And remember that when in resonance, for example, a free problem, the two reactances cancel each other, so that the damping relies only on the real part that could be viscous or some other model. But the physics interpretation, well, I'm confused, sincerely talking. As this is new to me, I have to think on this. But a part is always present, alpha of the stiffness, and maybe only the right-hand side impulse we must consider, because we go from time greater or equal to 0 in each cycle. Of course, we are out of constant coefficients, obviously. Because of the negative sign, the negative peak at the right of the time equal to 0 in the image you saw earlier becomes positive. So it seems that when the mass starts its motion, there's a surge in resistance that extinguishes right after, plus a constant quantity of the stiffness. This is maybe related to the model proportional damping, but somehow here I expressed what is exactly in time domain. However, the physical dimensions of the two terms in time are correct because the dissipative term has this physical dimension, Newton, and the dissipative, the damping coefficient has kilogram on, once again, kilogram on seconds or kilogram over seconds, I don't know. And if you take the dimensions of k on 2 sine of t, you end up with the same dimension, as you can see. The mass times the derivative of delta 2 has the same dimension, physical dimension. You can notice the typical dimension of a mass flow rate, which is kilogram over second, and we will come back on this topic later. As physical dimensions of derivative of Dirac delta, I put the inverse of time because they are, more than it is, two deltas, one opposite to each other and one after each other. Hence, the physical phenomenon, the physical dimensions, sorry, are the ones of the Dirac delta. So, damping coefficient, real part, the frequency independent case in first place. We now face the real part. If it's constant in frequency, we have this formula. Now, if we check the physical dimension, we have to observe that C is a mass, because, as usual, delta has 1 over the time, 1 over seconds, 1 on second, I don't know. So, because it is a kilogram on seconds, over seconds, we determine that C is a mass. So, about the physics interpretation, we know that an impulse causes a jump in velocity. Well, we could think that this is a negative jump of velocity that occurs at each half cycle or cycle. Maybe the jump in velocity is computed between the cycles, or maybe the difference is calculated between half cycles. Specifically, the jumping velocity is equal to 1 over mass on mass. I don't know. So that if we multiply this 1 over mass by a mass, it's a unit jumping velocity, and this seems quite interesting to me. Hence, the final situation for the case of frequency-independent damping coefficient real part is this one. We put together the two pieces and we obtain with this equation. I write again the formula here. It's obvious that I have many doubts, above all on the real part that in frequency becomes a mass. But if you think at a free damped 1 degree of freedom system, that should mean that at each cycles I lose momentum, and that is reasonable somehow. I'm not sure also about writing both inverse Fourier transform of zeta or impedance and force with negative signs. Maybe only one is correct. However, now let's think if real part is frequency dependent. So various thoughts have populated my mind. Here are some ones of them. If we consider the physical dimension, that is to say kilogram on seconds, we can write mass over time and all the chain of equals, and which is exactly mass flow rate, but as this quantity is multiplied by the velocity, we have a non-linear relationship once again. And above all, if we consider an alpha factor and the coefficient, drag coefficient, we end up dealing exactly with the aerodynamic drag force. And that makes sense, because if you think at a free damped oscillator or at a pendulum, the air resistance is the measure factor to slow down the mass, hence its front area. If the mass moves in honey, for example, you understand by yourself that the density is correct in the formula and plays a role. But again, we are out of linearity. Another idea I came up with was the following. If we consider kinetic energy and we imagine that damping is the property of decreasing speed, we can try to find damping force formula starting from kinetic energy. So energy is work, maybe in English, and force times distance. So force is derivative of energy on distance. So work is equal to energy, kinetic energy, the two expression for final initial kinetic energies. And then you shift